Hi, I'm Nagler. Thanks for stopping by. So there is universality in percolation, right? But is there a concept which sort of unifies continuous and discontinuous percolation, hybrid percolation and explosive percolation? The answer is yes. And this is what I would like to discuss with you with my contribution here. This is joint work, and the main merits deserve Unifying fun. Percolation can make you smart if your neurons connect, which is their nature. That can be good for you. Percolation can also make you sick, as we have all experienced last year, and that we were gonna experience this year. And there are a lot of models. So in general, we have the order parameter versus the control parameter, and typically percolation is continuous, in particular in the limit of n to infinity of large system sizes. So, but some percolation models here show discontinuous transition, meaning at a transition point RC, the order parameter jumps to a value of SC, which is larger than 0, and there's the gap delta. And the known knowns are the exponents, which describes this phase transition around RC. In continuous percolation, they typically show universality, so meaning they're not dependent on the model details. They may depend on things like the dimension, but even this maybe goes away if you have a system which has a dimension larger than the upper critical dimension. But universality is also not always the case in continuous percolation. So exponents in explosive percolation and hybrid and discontinuous percolation do not show universality and depend on model details. So universal scaling in percolation did exist prior to our work, like many decades since the 50s, but it could not really unify continuous, explosive, hybrid, and discontinuous percolation. So the question is what to look at in order to unify percolation. And the old school problem is the order parameter and its fluctuations do not do it. So our contribution is the largest gap in the order parameter and its fluctuation do it. But how? So we assume finite size scaling, but with respect to 1, the largest gap, where it is, this position RC, the control parameter, and we look at how large this gap is. And we look actually at not the gap in the thermodynamical limit, but the gap as I will show you in the next slide. And the third quantity we look is how big the order parameter after the gap is, which we call SC. So yeah, the gap can be defined for a finite system from one step to the next. And then you can look for the largest of those gaps in the order parameter for a finite system, sort of before you take the thermodynamic limit. But you actually anyway don't do that in finite size scaling. You just like investigate how things are dependent if you increase the system size L. And here, if you have a lattice, L to the D equals N. Yeah, and then one can do a standard ansatz for these 3 quantities, which we did for the gap size, delta. We have some scaling ansatz, which is standard. The details do not matter so much. For the position, we have a scaling ansatz, which is pretty standard. And also for the order parameter, which is then defined sort of after the jump, if there is any jump. But for a finite system, there will be always a largest jump. So there will be always a largest jump, even for continuous percolation. Yeah, that makes sense, right? So what we figure out is then that we derive the scaling functions sort of from first principles and not so much for RC, so that is just like an assumption that is Gaussian distributed, but we derive it for the gap, delta, and SC, so the order parameter. And it turns out that these are described by a Gumbel distribution. And actually, we don't have to fit here too much. And typically, if you have a scaling function, which describes has everything together, all the exponents are appear in the scaling function, and then you plot the system size, or vice versa, you plot certain quantities against the system size, then you can fit the exponents. So everything is condensed or related to the scaling function. And typically you don't have an analytical expression, but we do. And that is the reason why we came up with something which is universal and would work no matter if the percolation process shows a discontinuous or a continuous or a hybrid or a explosive transition. And what you see is already when we did the work, after we did the work, this green curve here shows like a collapse of the data points for different system sizes, and everything works out quite nicely, and that is for continuous percolation. And now we have also description, an analytical description of the scaling function for continuous percolation. But it's the same for discontinuous percolation, because that's the reason why we call it universal. So it's also a Gumbel function for discontinuous percolation here, for this gap itself, but also for the order parameter, at least to certain approximations. And the position where all this happens, where the phase transition happens, RC, that is in both cases Gaussian. And these scaling functions which you see here, they are following from some first principle, but which is that. But before I tell you that is, so the scaling and fits for other models are also fine. So we have like many models which are continuous and discontinuous, and we prove that this holds more or less in general. So, and now I would ready to discuss something. So conventional percolation theory could not provide a consistent framework that unifies continuous, discontinuous, explosive, and hybrid percolation. And our theoretical framework unifies these domains by means of universal scaling function based on finite size scaling that we have seen, and extreme value statistics regarding the size of the largest one-step gap in the order parameter. So this one-step gap is an interesting quantity, because if you focus on it, you can unify percolation. So what is extreme value statistics, and why people typically don't look at this in the context of percolation? Well, usually this order parameter has more or less nothing to do with extreme value, right? So the largest component is often unique, in particular of standard continuous percolation. So, but you cannot really use extreme value theory, or can you? Or what is extreme value theory? Or actually, why nobody before came up with such universal scaling function after decades of research in the field? So what we do is we derive the scaling function of the largest gap from first principles and link it to the order parameter. Okay, so that is the trick. And we use extreme value theory, which is not an invention of us. This is out there very long. It just tells you, if you tells you a lot of things. If you have uncorrelated random variables, which are described by distribution, then this distribution, and you take the maximum for finite sample then the distribution of the maxima of the extrema cannot follow like any distribution. So there can only follow three distributions. And if you check which case is valid for percolation for the largest gap, which is an extreme value of this order parameter curve, right? Because it's the largest gap. And that's it. That is the idea. That is the reason we can use extreme value theory. That is the reason for the distribution of the gap. We have a universal function. And it turns out that it's actually the Gumbel function. So that is the reason why it's Gumbel. But how? So, of course, everyone can do scaling. Here I would like to show you the final slides, acknowledgements. Thanks a lot. And now let us go to the paper. Let us stop share here. And I share the screen of of Wikipedia. So extreme value theory. It's a little bit complicated, in particular if you want to prove something, but has something you do. You have like a sequence of independently and identically distributed random variables, which are drawn from some distribution. And now it just like depends what type of distribution you draw those random variables from. And then if you look at the maximum, there are three types. And either it's a Weibull law, it's a Gumbel distribution, or a Fréchet distribution. And for percolation, one can show that is a Gumbel distribution. But how you can show that? Let me open here that one here and then share you the screen. So, and now I go to our paper. So again, what paper is it? Universal gap scaling and percolation. And here you have the formula of how this gap is defined. Then you define some new exponents, this gap exponent, just like by finite size scaling, nothing dramatic with respect to sort of the fluctuations. And these are all standard ansatz. This is nothing sort of, let's say, out of the box. But what is nice here is the following paragraph. So, and let me shift my own picture. So for linking our framework to extreme value theory, we make two observations. For finite system of size n, close to RC, that is where the percolation transition takes place, the distribution of cluster sizes, n of s, typically exhibits the power law for cluster sizes up to a certain cutoff, because it's a finite size system, right? Related to the correlation length. So that is all textbook. For some models of continuous percolation, the cluster size distribution is given by sort of a power law with that Fisher exponent and then times an exponential law. So meaning the tail is always like going down rapidly. That sort of has to be the case. So whereas in general, the distribution may take a more complicated form. So some people always say it has to be this distribution. That is incorrect, but even for continuous percolation, but it looks sort of like that. In particular, you have like one factor which really killed sort of large-scale power law behavior. So in either case, for clusters much larger than this cutoff, and there must be a cutoff because it's a finite system, that is for S larger than this cutoff, the distribution decays rapidly. This is what I just said. So it decays rapidly. And what is rapidly? So the size of the largest gap is exactly given by the size of the second largest cluster in the entire range of the order parameter. So that may be trivial, maybe not for you. There's a paper, my own paper, you can read it if you want. So meaning if you look then at the second largest cluster, you know how big it can be, and it's quite limited. And because of this, since the second largest cluster is, however, much larger than the cutoff size, the largest gap size is necessarily characterized by the light-tailed part of the critical cluster distribution. So, and that we really need, this light-tailed part, because then we can plug it in extreme value theory. And this means that the distribution of largest gaps becomes necessarily sharp for a large system. This is one, and the largest gaps are maxima obtained from independent ensemble realizations, because this is what you do in ensembling in percolation, right? So you study the ensemble average. So thus, extreme value theory predicts equation 11, whatever that was here. So that is sort of the universal scaling function. But there's a specific form of this f of delta. And the specific form of this f of delta is this guy here. And here you see, it looks like Wikipedia sort of. You may have like a positive additive constant, which sort of has to be 0 for other reasons, which go back to many interesting physicists. This prefactor also doesn't matter so much. And we have sort of e to the minus e to the minus z minus z. And that is sort of something like the variance of this distribution. And here are the exponents which pop in. And that is too complicated for a 12 minutes talk. But yeah, why not studying this if you're interested? Thanks a lot.